little bit about inverse sine and inverse cosine, inverse tangent. So what you did with this exploration, let's first look at, here's your sine graph, and you were asked some questions about the range and domain. Your domain for your original sine graph, you should know, is negative infinity to positive infinity. Your range goes from -1 to 1. So when we create a sine inverse, this graph, if you remember from Algebra 2, remember when you create inverses of functions, you can do that in one of three ways. You can kind of switch out the x-y coordinate pairs. You can look at an equation and just switch the variables, replace x with y, or replace y with x. Or you can take the graph and reflect it across the line y equals x. And that's what we're doing here. So if we look at the graph of, here's y equals x, here's our original sine graph. This blue graph is now the inverse of that. And what happens to that function, when we reflect that across the line y equals x, the inverse that we get is not a function because it doesn't pass the vertical line test. Okay? So mathematicians wanted to define an inverse of the sine that would also be a function. Okay? So what they decided to do was to eliminate some of the domain. If we focus just on the domain that goes from about right here, or just on the part of the graph that goes from about here to here, then we've created a graph, this black graph that I've created, passes the vertical line test. As soon as we start going beyond that, now it doesn't pass the vertical line test anymore. So I'm just going to erase that part. So we can create a sine inverse function, but we have to limit what we call the domain of the original function that it derives from. So if we take this original function, and remember on this axis for our original function, these values represent angle measures, and these are radians or degrees, and along the y-axis, that represents the trig ratios. So if I limit the domain of the original function, what I'm limiting is I'm going to say, okay, I'm going to make this graph only go from about negative pi over 2 to positive pi over 2, somewhere approximately there. And then when I reflect that across the line y equals x, and I look at my new graph, now its range is going to go from pi over 2 and then down to negative pi over 2. Okay, so that's what we were trying to get at in this investigation, is to try to get you to see that if I reflect the entire sine graph across the y-axis, the result is a graph that is not a function. If I reflect the sine graph across the y-axis, the line y equals x, and I've restricted its domain, then the result is a function. And the reason I want that to be a function is this. Take out your graphing calculators. I want you to run through a little something with me. If you would turn the mode to angles, or to degrees. Turn the mode to degrees. And then I want you to just find for me the sine of 30 degrees and tell me what that is. 0.5, okay, or a half, okay. And it's always a half. Doesn't matter, you could figure out the sine of 30 degrees a number of ways. It's always going to be a half. What about the sine of 150 degrees? What's that equal to? 0.5. Yeah, that's a half as well. And what about the sine of, 390 degrees? What's that equal to?
0.5.
How about that? All right. So that's okay. I mean, we can look at, so if I look at the sine graph, I could locate 30 degrees, and the sine would be about a half right here. I could look at 150 degrees, and the sine would be about a half. And I could look at 390 degrees. It's way out here somewhere on the graph, but the sine would be a half, okay? And that's okay. There's a nice, you know, for every x, there's exactly one y. Now, let's look at it from the inverse perspective. Let's look at the angle whose sine is 1/2. What do we get for that value? 30 degrees. Okay? Now, that's sort of interesting because the angle whose sine is a half is also 390 degrees. The angle whose sine is a half is also 150 degrees. Okay? But what we want is, we want to define an inverse function so that for this x value, there's exactly one y value. Okay? For every x, there's exactly one y. That's how you end up with a function. So that's kind of the long story to why there's only one solution in your calculator. When you do arc sine 1/2, you're only going to get 30 degrees. You're not going to get 150 degrees and 390 degrees. But you are all smarter than your calculators, and you know that there are other angles. So you can always use that as a reference angle to find the others. But your calculator is working like a function. It's working under the restricted domain of the sine graph. So let's take a look at, I'm going to pull up the notes now, and as we look at this, the first part of the notes really just discusses a little bit about functions and vertical line test, and I'm going to scoot past some of that because it's really kind of Algebra 2 material. And let's get right to the inverse graphs. This is what you were studying in your investigation. So we start with a sine graph. We're going to just take part of that sine graph from about here to here. I'm going to just truncate that sine graph, and that's what's pictured right here in this middle graph. There's our sine graph with the limited domain, or restricted domain. The domain is only going from -π/2 to π/2. And when we invert that across the line y equals x, if I was going to kind of sketch that, there's like y equals x. Here's my new graph, and it's a little bit stretched in this image right here. But the idea there is you now have a sine graph, and on this axis, instead of being the angle measures, now these are the trig ratios. So your graph goes from -1 to 1 because we know that the sine function goes from -1 to 1 in the y direction, your typical sine function. And then your angle measures are going from -π/2 to +π/2. Okay, -π/2 to +π/2. That's where the inverse sine is defined. And that works well because in this region from -π to π/2 to π/2, we only have, you know, certain angle measures depicted, but we have every sine ratio from down here at -1 all the way up to +1. So you could type in any given sine ratio and always come up with an angle, okay? All of the negative sine ratios are included, and all the positive sine ratios are included. If we look at this graph, this is where all the negative sine ratios would be. This is where all the positive sine ratios. And for all of those possibilities from -1 to 1, your angle measures are going from -π/2 up to +π/2. So this is kind of a long-winded discussion about, you know, how mathematicians define these inverse functions, and then we're going to use them, okay? I think it's important for you to see the background and see where this all comes from, because that'll help you remember where these various trig functions are defined, but you don't have to feel like you're responsible to reproduce any of this, because we're going to apply it actually. So the next graph we looked at was the inverse cosine. So here's your you know, basic cosine graph, where the mathematicians decided to chop off the cosine function happens to be between 0 and pi, and between 0 and pi we get every possible cosine trig ratio from +1 down to -1. So here's that graph truncated, and now here's that graph when we reflect it across the line y equals x. Okay, so The domain for the cosine graph goes from 0 to pi, or excuse me, for the inverse cosine graph is going to go from 0 to pi. So we restrict it from 0 to pi, and then when we invert it, that now becomes our range, but those values are from 0 to pi, unlike arcsine, which went from negative pi over 2 to positive pi over 2. Teddy?
Why aren't you starting with 0 and going to pi?
Okay, if we went all the way to 2 pi, then when we invert the graph, now we no longer have a function.
All right.
Okay? That's a good question. Okay, let me show you the tangent inverse, and some of you got this far in the exploration. With the tangent inverse, it was a little bit easier. They didn't have to really think about chopping the graph, but they just chose one period of the graph, which represents all the possible tangent values, and the period they happen to choose is this period that's right in the middle, and that goes from negative pi over 2 to positive pi over 2. So the domain of our limited or restricted tangent function goes from negative pi over 2 to positive pi over 2. And then when we reflect that across the line y equals x, we get this graph right here. Okay? We have that graph. So now the domain for, the restrictions on the domain for inverse tangent are from negative pi over 2 to pi over 2. So the new range for the inverse tangent is going to be negative pi over 2 to pi over 2, because the x and y information just reverses. All right, so that's kind of a lot of explanation. Let's see what we're going to do with this. First of all, I've put together a little chart for you to copy down or come back to this in the notes kind of at your leisure. But this is going to be really important because this is where the inverse trig functions are defined, and this you will probably want to use frequently. So if we think about labeling the graph, this is going to be 0 in terms of the angle measures. This is pi over 2. Over here we're at, that should be pi, not negative, sorry, that should be positive pi. And then down here we're at negative pi over 2. And so I told you that the restrictions on the inverse sine function were from negative pi over 2 to positive pi over 2. So that's why arcsine is listed in those two quadrants, from negative pi over 2 to positive pi over 2. So this is kind of a nice little graphic just to kind of help you remember where the inverse trig functions are defined. Our cosine function is defined in the first and second quadrants, or from 0 to pi. And that corresponds with what we just talked about on the graph for our cosine. And then the arctangent, like the arcsine, happens to be defined in negative pi over 2 to positive pi over 2. So those are the values where you'll find arctangents. Here in the fourth quadrant, the x values are negative. So this is for arcsine and arctangent that have negative trig ratios. The first quadrant is for arcsine, arccosine, arctangent, where their trig ratios are all positive. And then the second quadrant is for arccosine, where its trig ratio is negative. So you can see there's all the possibilities. We can have positive or negative trig ratios for cosine, positive or negative trig ratios for sine, positive or negative trig ratios for arctangent, and it gives you just a chart to help you keep all this information in your head. So one of the things you're going to be asked to do is to draw reference triangles to help you identify, for instance, the solution to, or what does arcsine 1/2 represent. So what you're going to do is look first at the positive or negative value of the trig ratio. Since it's positive and arcsine is positive in this quadrant, we're going to go to the first quadrant. Plot your reference triangle. Remembering, now we're going back to reference triangles and SOHCAHTOA. So we're going to recall SOHCAHTOA here, and we're going to remember that for sine, it's the opposite side over the hypotenuse. So that's why I'm going to label my triangle here. I'm going to label it opposite over hypotenuse. hypotenuse. It's positive, you know, this ratio is positive, I'm in the positive quadrant. I recognize that as a 30, 60, 90 triangle, and so I just label this angle right here. I'm going to call that 30 degrees, and that tells me then that the arc sine 1/2 is equal to 30 degrees. So I can simplify an expression like this. I can kind of solve it by drawing a reference triangle. But I just have to be sure my reference triangle is in the right quadrant, depending on whether the inverse function is positive or negative, or whether the trig ratio is positive or negative. So I'm going to jump over and look at the arctangent. This one, the trig ratio is negative. Arctan is defined in the first and fourth quadrants, but it's negative in the fourth. So I'm going to draw my reference triangle in the fourth quadrant. And I have here opposite over adjacent. And remember, that comes from SOHCAHTOA. So we're going to have the opposite side of the triangle is 1, the adjacent side is √3. I have to put that negative sign somewhere. I'm going to put it with the 1 because that's negative in the fourth quadrant. And then again, I recognize that as a 30, 60, 90 triangle. And since arctangent is defined from negative pi over 2 to positive pi over 2, I have to name the angle in that range of values. So I'm going to call this angle negative 30 degrees. And you can check that in your calculator right now. If you type in arctangent negative 1 over √3, be sure you put that in parentheses. You should get negative 30 degrees as your answer. Anyone confirm that? You got that? Okay. I'm going to move, let's see, I guess I'll do this one last example here with the √2 over 2. Since we're drawing reference triangles by hand, we're expecting to find the triangles that either are the 30, 60, 90. Okay, remembering our ratio of sides here is going to be 1, 2, √3. Or we're going to expect to find a right triangle that is 45, 45, 90, where our ratio of sides is 1, 1, √2. And looking at this ratio, it doesn't really look like either of those, but you may remember from some previous problems, one of the things we did occasionally was to rationalize the numerator, and then that allows you to see this in a little different way. Now we have arc cosine of negative. This is going to simplify to 1 over √2, and then we can just draw the reference triangle for that. Okay, remembering that when the trig ratio with cosine is negative, we draw our triangle in the second quadrant. This is where you need to use this chart. Okay, so I'm going to draw a triangle where the adjacent side, I actually did want to draw that more like a 45, 45, 90. I'm going to sketch this like this. So I have 1, 1, √2. And again, I have to put the negative sign someplace, so I'll put it right here. And now when I'm naming the angle, cosine is defined from 0 to pi, or arc cosine is defined from 0 to pi. So I want to name this angle right here. So arc cosine negative √2 over 2 is going to be named 135 degrees because this little reference angle right there is 45 degrees. Okay, so we've done a little bit of work drawing reference triangles by hand. You've been doing a little bit of work figuring out the inverse trig function values using your calculator. So you should be able to draw the reference triangles to help you figure out inverse functions. You can also use your calculator. Let me see what's coming up next here. This next part is just a quick little reminder that when you're evaluating arc cosine or arc sine, remember this expression or this notation means it is an angle measure, okay? It's an angle in degrees or radians. It's a measure of an angle. This is a measure of an angle. It's an angle that has a sine of 0.99. This is a measure of an angle. It's an angle that has a tangent of negative 1.25. So if you want that angle in degree measure, put your calculator in degree mode. If you want that angle in radian measure, put your calculator in radian mode. Okay? We are almost out of time, so I think what I'm going to do, I've been recording this because some of my other students today missed class. So I think I will record the rest of this lesson. There's a little bit more to it. So if you're having trouble with the homework tonight, if you can't figure it out on your own, I'll come back and look for the recording online and I'll have that for you. Joey.
For back to the trading or the trade thing.
Yeah.
B, like just like any one of them, wouldn't you have to assume that it's invariant since it doesn't have the degree?
No, because this now is the trig ratio, okay? You're used to thinking about, if I have sine of 30, I need to think about that that's 30 degrees. But this is arc sine of some value, of 0.99. So this is an angle. This is a trig ratio. That's a great question. Yes, turn in your papers as you walk out and be sure you put your computers away, please.